Well, thank you, Angela, and well, thank you to Angela, Monica, and Miles for the invitation to speak, but also for taking the effort to organize an extraordinary seminar during extraordinary times we find ourselves living in. So what I want to talk about today is really a family of PDEs, and they generalize the Yamabe equation. So although the PDEs have been around for about 20 years, and there's been a considerable amount of work on the subject, it turns out that in some really important contexts, there's still a lot that we just don't understand. And that's what I really want to talk about today. So this is a PDE seminar, and I imagine the audience is fairly broad. So although at the beginning, I'll spend a little bit of time trying to explain a bit of the geometric background, for the most part, I'm just going to emphasize the PDE aspects. And because it turns out that's where we have the most profound ignorance. And I also want to make it more of a survey. So as we're going to see, these PDEs are fully nonlinear equations. It can be extremely technical. If I were to get into the regularity theory, for example, it could be quite a mess. So I just want to try to give you a rough idea of where the PDEs come from, what are some of the issues, how are they like the Yamabe equation, how are they different from the Yamabe equation, and what are some of the critical behavior that you witness in these things. Okay, so for that reason, let me just begin with a quick sort of recap of the Yamabe equation, with my apologies to those of you in the audience who are experts on this. I won't spend a lot of time, but this is going to set up some important contrasts with these generalizations I'm going to introduce later. Okay, also, as much as possible, I want to write all my PDEs just on Euclidean space, so you can think of most of what's going to be happening and most of the interesting behavior that when trying to understand is just local things going on in Euclidean space. I mean, they come from the Riemannian setting, but for most of what I'm going to say, it's perfectly understandable just to write everything down in the flat case. Okay, so here's the Yamabe equation, well known. So it's a semilinear PDE and with a critical exponent on the right-hand side. Sorry, well, this is my first typo, hopefully not of many. So we seek solutions of the semilinear PDE, and we want positive solutions generally. And why do we want positive solutions? Well, there's a geometric interpretation to this PDE. Of course, actually, this PDE shows up in a number of contexts, but let me emphasize the geometric one, because that's related to what I want to talk about. So if you take the flat Euclidean metric and you multiply it by a power of your solution of this equation, all right, then you can compute the scalar curvature of this new metric. And then it turns out that it's just equal to the Laplacian times a different power of this conformal factor. And so what you realize is that, well, if you can solve the Yamabe equation, then what you've done is you've constructed a Riemannian metric that's conformal to the flat metric. And moreover, by looking at this formula for how the scalar curvature transforms and comparing it to the PDE, you realize what you've done is constructed a metric with constant scalar curvature. Okay, now, of course, the setting that, for which the name of the Yamabe is attached is on a compact Riemannian manifold. So on a compact Riemannian manifold, you have to change these formulas, but not by much. So now if you have a Riemannian manifold MG, so now instead of the flat Euclidean metric, you just have a general Riemannian metric. You multiply by power, and it's written this way just to make the equation nicer. Then the formula for how the scalar curvature changes is very similar. So now the scalar curvature is again that power, and the only difference at all is that you change the operator. So instead of the minus Laplace operator, it's minus Laplace operator plus this linear term involving the scalar curvature of the metric G. And this operator is called the conformal Laplacian. Okay, so therefore on a compact manifold, the equation you want to solve is in place of the minus Laplace V equals a power of V. Now you want to solve the equation where we replace the minus Laplacian with the conformal Laplacian. And how do you solve this? Well, this turns out to have a variational formulation, which is crucial for the solution of the Yamabe problem. So you can write down this natural Lagrangian, and solutions of the Yamabe equation are given by critical points of this functional. So again, I'm trying to emphasize the PDE aspects, and I want to not say too much about the geometry, but there's another way you could think about this Lagrangian that's well known. So in the numerator, this Dirichlet form associated to the conformal Laplacian, that's really just the total scalar curvature of the integral of the scalar curvature for the metric, conformal metric defined by this function v. And in the denominator, it's the volume. So it's really a normalization factor. But anyway, the point is that this is a variational PDE. Okay, as is well known, there are these 4 canonical names associated with the solution to this problem. So the idea was to use the direct variational approach and try to prove the existence of a minimizer. So it originated with Yamabe in 1960. And Schrödinger, is well known, found an error in Yamabe's paper, patched up part of it, and then the remaining cases were recovered by Aubin and Chang. Now, okay, so after that quick review, let me just emphasize a couple more things that will be relevant for these generalizations I'm going to talk about in a minute. And one of the most crucial things is the sign dichotomy. All right? So if you define the Yamabe invariant to be the infimum of the Yamabe functional, the least energy of the minimizing solution, then it splits into 2 cases. All right. If the least energy is non-positive, right, then the existence theory is fairly straightforward, and moreover, if you get a solution, it's unique. Okay, so this is the easy case. By contrast, if the Yamabe invariant is positive, this is the hard case. All right, so now the existence theory is quite difficult. You have to worry about bubbling, for example. Moreover, if you find a solution, it may not be unique. I guess it was Rick Shane who first constructed multiplicity results. And later on, it was discovered that, in fact, the solution space may not even be compact. Right? So dramatically different depending upon the sign of the scalar curvature or the Yamabe invariant. Okay? Positive, non-positive versus positive. And we're going to see a similar dichotomy for these generalized Yamabe type equations. Okay, so and then couple last comments. So of course, typically you don't try to do the direct method. What you do first is you regularize the problem by lowering the exponent, solving that problem because you build in some compactness that way, and then try to study the limits of those solutions. But now let me say something that in the context of the Yamabe problem is a little bit silly, but again, when we get to these generalized Yamabe equations, this will be an important point. If you have a sup norm bound, say on a ball radius 1, then because the Yamabe equation is semilinear, you can control the solution and all derivatives of the solution on any smaller ball. Okay, so again, this just follows from the equation being semilinear. The generalizations we're going to talk about are fully nonlinear, and this kind of estimate where once you control the L infinity norm, you're done, does not hold. So we'll come back to this later. Okay, now before I can really introduce these generalizations of the Yamabe equation, it's better if I spend a little bit of time talking about some classical models of fully nonlinear PDEs. So let's begin talking about the Monge-Ampere equation. So take a domain in Euclidean space. I'm not going to be talking about any kind of boundary value problems. I just want to define the equations. So for a C2 function, let nabla squared denote the Hessian matrix. Then the Monge-Ampere equation is the equation that prescribes the determinant of the Hessian. Okay. Now you can generalize this to have the right-hand side depend upon u or the gradient of u, et cetera, but this is more in its most basic form. This is the Monge-Ampere equation. Okay, so this equation is fully nonlinear. So in other words, it's nonlinear in the highest, which is to say in this case, second order derivatives. Okay, so if you linearize this equation, so you have a solution, you linearize at the solution, and you look at the linearized operator, then the coefficients of the linearized operator at the highest level, so the symbol of for the linearized operator, the coefficients will depend upon the second derivatives of the solution. Okay, so if you want your linearized operator to be elliptic, you're going to have to impose conditions on the Hessian of your solution. Okay, so the Monge-Ampere equation will be elliptic provided that your solution U is convex. Right? So that'll, if you linearize at a convex solution, then the linearized operator will be elliptic. And the ellipticity constants of the linearized operator will depend upon the second derivative estimates for your solution. Okay, so you get ellipticity if it's convex. Now, you can also assume it's concave. So if you have a concave solution, then if you linearize, then you can look at the symbol of the linearized operator. And now what will happen is, okay, the symbol will be non-degenerate, but it could be negative definite instead of positive definite, for example. But so it doesn't matter, but it's easier just to say, well, look, if you're concave, just switch U with minus U. And now you have something which is convex. And so we may as well just stick with convex solutions. All right. Now, the Monge-Ampere equation is just one example of an equation in which you prescribe some function of the eigenvalues of the Hessian. So a little more generally, we have what are called the Hessian equation. So to introduce that, I'll need a little bit more notation. So in general, if I have a symmetric n by n matrix, then it's going to have n real eigenvalues. And so what I want to do is look at different symmetric combinations of those eigenvalues. So I'm going to let sigma k denote the kth elementary symmetric function. So this is just in n variables, you just take all k-fold distinct products of your variables. So if I'm given a symmetric matrix, I can compute its eigenvalues. I have n eigenvalues, and I can plug those into the symmetric functions. And this gives me sigma k of a given matrix. All right, so sigma k makes sense as a function on Rn, but it also makes sense as a function on the space of symmetric n by n matrices. So for example, if k equals 1, what I'm doing is I'm just summing all the eigenvalues, so I just get the trace, right? And if k equals n, I'm multiplying on the eigenvalues, so I'm looking at the determinant. Okay, so the Hessian equations, what they prescribe is the kth symmetric function of the eigenvalues of the Hessian. All right. So this is a generalization of the Monge-Ampere case. So when k equals 1, you're taking the trace, right? So that's Laplace U equals f. That's Poisson's equation. When k equals n, you're taking the determinant. You're back to Monge-Ampere. Okay. All right. What about ellipticity here? So it's a little more complicated for algebraic reasons, but it's fairly easy to state. So if you linearize at a solution, what do you need to get the ellipticity for the linearized operator? So the condition that works is if you assume the Hessian is, instead of being convex, you can have a weaker condition for k less than n. You need k, what's usually called k convexity. So in other words, what you need is one formulation of it. Excuse me. You need that all the symmetric functions of the eigenvalues up to degree k are all simultaneously positive, right? So if you have that, then the linearized operator will be elliptic. So shorthand notation for that is going to be, we'll write that the Hessian is in this set, all right? This is just saying that all the eigenvalues, if you think about it, you have n in real eigenvalues, you can think about it as a point in Rn, and you want to say that point in Rn is in the set of all points in Rn that satisfy these conditions. Now, I mentioned that in the Monge-Ampere equation that you can consider convex solutions or concave solutions, but it amounts to the same thing just by replacing U with minus U. All right, similar thing here. So if minus U is k convex, you still get ellipticity, but again, just replace U with minus U and you go back to the k convex case. So there's no reason to worry about minus the Hessian being k convex. It amounts to the same thing. Okay, so that's a quick introduction or reminder, depending upon your background, on the Hessian and Monge-Ampere equations. So now I'm ready to talk about these generalizations of the Yamabe equation. So again, I'm just going to do some Euclidean space. We'll get what it looks like in a Riemannian manifold in just a second. Again, it's not that different. So given a C2 function, now we want to define this matrix, which I'll denote A with a subscript U, because it's dependent upon U. And you can think about this as a nonlinear version of the Hessian. All right, so the leading term is the Hessian. So subscripts here mean partial derivatives. So the leading term is the Hessian, but then I have these terms that are nonlinear terms. So they're quadratic in the first order derivatives. Right? So it's the Hessian plus some nonlinearity in the gradient. Okay. So the equation I want to consider, I'll call it the sigma k Yamabe equation. I'll explain why we still use the word Yamabe here, is the following generalization of the Hessian equations. All right, so the Hessian equations that we talked about before, you look at the kth symmetric function of the Hessian. Here, what we're going to do is look at the kth symmetric function of this nonlinear Hessian. Okay, and then what's more, on the right-hand side, we're going to allow this exponential nonlinearity. So it's the Hessian equations in the simple case, but modified by two additional nonlinearities. Okay, so we have the nonlinearity in the matrix here, coming from these terms that are quadratic in the gradients, and then the right-hand side, I have this other nonlinearity. Okay, now one way to see why this is somehow connected to the Yamabe equation is to write this down when k equals 1. So when k equals 1, if you take v to be this power or this exponential power of u, then this actually does reduce to the Yamabe equation. So it just happens that for these generalized equations, there's no canonical way to write the PDE. So for the Yamabe equation, if you think about this in the geometric context where you're writing down your conformal factor, so basically there's one power that makes the equation semi-linear in a nice way where you do not see any gradient terms. So for these generalizations we're going to talk about, there's no nice way to get rid of the gradient terms. They're just always there. So for other reasons, it tends to be nicer, or at least I prefer to write the conformal factor in exponential form. So that's why when you go from these generalizations to the regular Yamabe equation, you have to sort of change the power. Okay. Anyway, these are the PDEs we want to study. Okay. So again, just to repeat what I said a minute ago, it's a generalization of the Hessian equations, but with these additional nonlinearities. So what I want to talk about is the following. So there's sort of two criticalities going on in these PDEs. So like the Yamabe equation, the exponential nonlinearity on the right-hand side, so if you write it in terms of power, it's a power nonlinearity, it is also critical. All right, it's not obvious writing it this way, but if you think about the scaling behavior and the dilation properties of the PDE, you can see why this is critical. For the same reason, it's related to the criticality for the Yamabe equation. I shouldn't say it's the same reason. And then there's this other criticality. So it turns out, and this will take me a little time to explain, but it's really crucial for our understanding of this PDE, is that in some sense, this quadratic nonlinearity in the gradient is subcritical, okay? So I'll make that more precise later on. So we have two criticalities. This is critical, this is sort of subcritical. Okay, so what about ellipticity? Well, it's going to be analogous to what we saw for the Hessian equation. So for the Hessian equations, they were elliptic, provided that the Hessian matrix was k-convex. Now we need this nonlinear Hessian matrix to be k-convex, and then the linearized operator will be elliptic. And once again, you can replace. So you can assume that this is the nonlinear Hessian is k-convex, or you can assume that minus the nonlinear Hessian is k-convex. All right. So here's your two ellipticity conditions: either the nonlinear Hessian is convex, or minus it is k-convex. And now it turns out that's actually an important difference. So, go back to Monge-Ampere. I said, okay, you can consider convex or concave, but it doesn't really matter, because if you're concave, just replace u with minus u. Well, here, because of this nonlinearity, it's not the same thing, just trying to replace the solution with minus the solution. So I'll come back to that in a minute, because it's going to really be the beginning of a bit of a long story. But for now, let me just mention that the ellipticity is a little more complicated here. All right, so I mentioned that I want to emphasize the PDE aspects, but to understand where these equations come from, let me just spend a few minutes just talking about the geometry. I'll try to be as brief as I can, but still give you a flavor for what's going on. So here's the geometric interpretation. The PDE doesn't look that different, actually, but to understand where it comes from, it takes a few minutes to explain. So if you have a Riemannian manifold, so you have the Riemannian curvature tensor, and then you can look at various contractions of the curvature tensor. So you have the Ricci tensor, for example, which is a bilinear form in the tangent space at each point. And then you can trace that or contract that, and you have a scalar function. All right. So then you can take some combination of the Ricci tensor and the scalar curvature and define what's called the Schouten tensor. Now, if you haven't seen this before, I'll explain in a minute, roughly speaking, why it's important. But if you have seen before, you know that this plays a sort of fundamental role in conformal geometry. Okay, this is a bilinear form, just like the Ricci tensor, but there's a canonical way to associate to this bilinear form using the metric tensor a linear map of the tangent space at each point, a symmetric linear map, in fact. So this is the conventional notation for this. It's just because if you, I mean, this is algebraic. So if you take a bilinear form and then you want to write down the matrix for the associated linear map, and if you write it down local coordinates, you'll see that what enters into the formula is the inverse matrix for the metric tensor. So for that reason, this is sort of the shorthand notation for the associated linear map at each point. Okay, so you have a symmetric linear map on the tangent space, therefore it has n real eigenvalues, and so you can take the kth symmetric function of the eigenvalues of the Schouten tensor, and that is called the sigma k curvature. Right, so you take the kth symmetric function of the eigenvalues of this associated linear map. Okay, so what does this mean? Okay, well, when k equals 1, it's just the scalar curvature. So you're just tracing the Schouten tensor, and if you look at the definition, it's not difficult to see that you're just going to get some dimensional constant times the scalar curvature. What about for other values of k? Well, let me just tell you in a couple model spaces what's going on here. So, for example, take the sphere with a standard round metric. Then it turns out that the Schouten tensor is diagonal. All right, so it has eigenvalues all equal to 1/2. So the Schouten tensor, unlike the Ricci tensor, is the definition is set up to make it sort of dimension free. So the eigenvalues are always 1/2, and it doesn't matter the dimension of your sphere. Okay, so it's just a diagonal matrix with all entries 1/2. So if you compute the kth symmetric function, it's just how many k tuples you have of eigenvalues, and so this is what you get. On the other hand, what about hyperbolic space? Take the other model space of constant curvature. Well, now all the eigenvalues of the Schouten tensor are -1/2, so you get the corresponding formula. Okay. So for the constant curvature spaces, the sigma k curvature is constant as well. Okay, so let me try to get this back to the PDE we're studying. So the Yamabe equation is about studying what happens to the scalar curvature under conformal change of metric and prescribing the scalar curvature. So for this generalization, the sigma k Yamabe problem, what you're going to do is look at the sigma k curvature. Right? So what you have to do is see how the Schouten tensor changes under conformal metric. So if I write my conformal metric this way using exponential notation, then this is how the Schouten tensor changes. So the Schouten tensor with respect to your conformal metric is the Schouten tensor with respect to your background metric, plus, and the leading term is the Hessian, and then, but there's these quadratic terms in the first derivatives. All right, so that's where this equation is coming from. This, what I'm calling the nonlinear Hessian matrix, is really just the conformal Schouten tensor. Okay, so what we're trying to do is prescribe the sigma k curvature of a conformal metric. So that's what the sigma k Yamabe problem is. All right, and of course the classical Yamabe problem is just a special case. When k equals 1, you're just talking about prescribing the scalar curvature or the sigma 1 curvature conformal metric. But you can look at the other values of k. So these are geometrically natural equations, it turns out, for many reasons, and for reasons that actually are fairly involved to explain. But let me just point out, okay, where does the Schouten tensor comes from? So the easiest way to say it is the following. So the Riemannian curvature tensor, in higher dimensions anyway, is this complicated algebraic object. It's a 0-4 tensor in one possible interpretation of it. On the other hand, the Schouten tensor is algebraically much simpler object, right? Just a bilinear form. Nevertheless, if you want to calculate how the full curvature tensor transforms under conformal change of metric, it turns out it reduces to just understanding how the Schouten tensor changes. Right? So somehow you're capturing all the information just by looking at the Schouten tensor, and then by looking at the symmetric functions of the eigenvalues of the Schouten tensor, that's sort of capturing some kind of information about how the full curvature tensor is changing. Okay, all right, so let's pull back from the geometry. Now let me get back to the PDE to sort of explain what do we know, what's unknown, et cetera, et cetera. Oh yeah, sorry, one last thing. I jumped the gun there. So this is not so important, but I mean, it's interesting contrast with the Yamabe problem. Okay, what about ellipticity? It's going to be the analogous thing. So the PDEs, when we wrote them on Euclidean space, we said, okay, they're elliptic provided the nonlinear Hessian matrix is K convex. Okay, so the analogous thing in a manifold is that the conformal Schouten tensor is K convex. And I just want to point out that that's actually, that can be, once K is bigger than 1, that can be a very strong condition. So one important departure from the Yamabe problem for these equations is the following. You give me an arbitrary Riemannian manifold, I can at least try to solve the Yamabe problem. It makes sense. All right? You can, in other words, it's known that there's no way before the solution to the Yamabe problem, you can easily prove that every conformal class admits a metric of positive or 0 or negative scalar curvature. All right? That's not going to be true for these sigma K curvatures. Right? Those are obstructions to admitting metrics with sigma K curvature having a fixed sign. So let me just here's a very simple example to write down. You don't have to get very exotic here. So just on the manifold S2 cross S1, you're never going to find a metric for which the eigenvalues of the Schouten tensor are 2 convex. They don't exist. Okay, and it also, I should have written here as well, or minus the Schouten tensor is 2 convex. It imposes a strong condition on the curvature, and then for topological reasons, you can rule it out on this product manifold. So this is a little bit different than the Yamabe problem. I mean, there's a geometric constraint that you first have to deal with. All right, but that will not be relevant for anything I'm going to say from now on. I just wanted to, for the purpose of completeness, mention this. Let's get back to the Euclidean space, and let me just try to explain what's going on with that PDE. Okay, so, and now we come to this crucial thing I want to emphasize about this ellipticity condition. So let's suppose we have a solution of this PDE wrote down earlier. Right, here it is again. Right. So this is prescribing the kth symmetric function of the eigenvalues of this nonlinear Hessian matrix. And then the right-hand side, I've got this exponential nonlinearity. Okay, so let's suppose we have a solution, and it's an elliptic solution. All right, so I'm assuming that the eigenvalues of the nonlinear Hessian matrix are K convex. Okay. Now, by contrast, suppose I have a solution for which minus the eigenvalues of the nonlinear Hessian matrix are K convex. Well, let's do what we mentioned doing for the classical Hessian and Monge-Ampere equation. Let's replace U with minus U. So let's give it a new name. Let's call W equal minus U, right? Then what happens? So I'm going to rewrite the PDE in terms of this new variable W. And I get this. Like the equation above, in both cases, so up here, this matrix is K convex. Down here, this matrix is K convex. This constant is positive, this constant is positive. That just falls from K convexity of the matrix you're taking the K symmetric function of. And then notice the exponential nonlinearities change sign, obviously. So the point is, what I want to emphasize is that they're really different equations, all right? Now, you might say, well, wait a second, you just took a solution and you put a minus sign in front of it. You're trying to tell us it's a different PDE. This is crazy. But the point is the convexity condition, all right? If you impose that the matrix that you're taking the K symmetric function of is K convex, right? That's an additional condition on the PDE, okay? So yeah, you could argue it's the same PDE, but the convexity condition changes. So by doing the sign change, what you're really doing is saying that, okay, I'm going to impose the same convexity condition, but then I'm going to change the PDE, right? So this is so I call this PC, you're usually referred to as the positive cone condition because your matrix is K convex. This is NC, or negative cone equation, because you're assuming that the nonlinear Hessian matrix is negative, or minus that is K convex, right? So they're different PDEs. And I want to spend a little bit of time here explaining why this PDE we know a lot about, and this PDE we essentially know nothing about, okay? Okay, so where did this come from? So I mentioned these PDEs have been around for about 20 years. So they were introduced in the thesis, PhD thesis of Jeff Viaklowski. So really, it's kind of a weird story. I mean, his advisor is Phil Griffiths. So, you know, the algebraic geometry. So it's a bit odd that this was the thesis project, but anyway, it was the beginning point of a lot of interesting work. So the formulation is basically, we've already seen it. So given a compact manifold, let's assume that the Schouten tensor is K convex, and we want to find a conformal metric for which the sigma K curvature is constant. All right, and we, of course, we want to keep the PDE that that determines this elliptic. We're going to assume that the Schouten tensor for this conformal metric is also K convex. Right. So when K equals 1, this is the Yamabe problem. So this is the generalization for other values of K. Now, as I mentioned, a lot of work was done on this PDE by a lot of different people. And so I could fill up a couple slides of names of people who did really interesting, important work on this. But if you specifically talk about this formulation of the sigma K problem, just trying to find solutions for which it's constant. So the rough list of names are given here. So, but it's essentially solved. But I should also mention that, you know, these works also relied on, you know, earlier work on, say, for example, proving, you know, a priori estimates for solutions, things like that. So there's a lot of background work behind this list as well. But anyway, the point is it's essentially solved. Okay, so but now let me point out some important differences with the regular Yamabe problem, the K equals 1 case. So first of all, it's not variational in general. So this is, so for example, a lot of these existence results, what they rely on is some sort of combination of degree theory argument plus a priori estimates. Right? There's blow up analysis involved, et cetera, but they're not variational. All right, so when I say that something is not variational, what do you mean by that? I mean, how do you prove something is not variational? Right? Well, okay, I mean it in a somewhat precise sense here. So think about the Yamabe problem, right? So we wrote down this the Lagrangian at the very beginning and said that the solutions of the Yamabe equation are critical points of this functional. And I said there's a geometric interpretation of this functional. It's the total scalar curvature. So you get constant scalar curvature metrics by looking at the Lagrangian that assigns the integral of scalar curvature to each metric in a conformal class. And then you normalize the volume, say. Okay, so if you try to do the same thing for the sigma K version, where you integrate the sigma K curvature and try to look at, use that as your Lagrangian, your Euler equation will not in general correspond to sigma K equals constant. So it's just different. When K equals 1, of course, it's true, it's the Yamabe equation. When K equals 2, Vyachelovsky showed in his thesis that it still works. So it turns out K equals 2 is a special situation. It's still variational for K equals 2, all right? Except in dimension 4. Dimension 4 is a special animal because, well, for various reasons, but in this context, because when K equals 2 in dimension 4, it turns out the integral of sigma 2 is conformally invariant, so it doesn't vary at all. That special case was handled by Chang-Han-Yang. Basically, they were still able to write down a Lagrangian whose critical points gave you constant sigma 2. So anyway, for K equals 1, it is variational. For K equals 2, it is variational. But Branson and Gover showed that that's it. I mean, they have this sort of meta argument that shows that you cannot write down some Lagrangian whose critical points, whose Euler equation has the kind of form you're looking for. All right. Okay. Now, a couple other weird departures from the regular Yamabe problem. So there was a long list of names associated to this solution. So why the long list? It turns out that unlike the Yamabe problem, this divides up into a lot more cases and has to do with the value of K versus the dimension. So for example, when K is bigger than half the dimension, that's one special case. So in that case, for example, it is known that the solution space is compact in any dimension. So this is unlike the Yamabe problem, right? So where high dimensions, you can have solution space may not be compact, right? Here it always is if K is bigger than half the dimension. Then there's this other weird thing about 4 dimensions. If you look at K equals 2 in 4 dimensions, solutions are unique, except on a sphere where you always have the action of the conformal group. So again, there's just nothing like this for the Yamabe problem, right? I mean, if you're in the positive case anyway, the negative case, of course, it's always unique. But you know, in general, it is not unique. Okay, and then what's the geometric interest in this? And so it turns out there's been a lot of applications to constructions of metrics of positive Ricci curvature, sphere theorems, pinching theorems, topology of conformally flat manifolds. So there's been lots of applications. Okay, so that's the that was the positive cone equation. So that's, you should think about it as like the positive version of the Yamabe case, which is a harder case. So that is basically solved. So what about for the negative cone equation? So now the negative, we're minus the nonlinear Hessian is k-convex. What do we know about that? And the answer is we essentially know nothing. Now you can do like a perturbation result or something like that, but I mean some kind of general existence result where you say, okay, if my Riemannian manifold satisfies these sort of natural properties, I can capture a solution. I know of no such result. Okay. Now here's one reason why that's kind of weird. So Vyachemovsky early on showed that, well, if you have a solution, you get this really nice a priori estimate. Right? The solution and its gradient have a a priori uniform bound. Just depends upon the background metric. Now, if you have this for the Yamabe equation, you're done, right? I mean, you have solution, you have a level of existence, a lot of compactness of the solution space, et cetera, et cetera. This is more than you need, in fact. But for these equations, because they're fully nonlinear, this is not good enough. Okay, so you need C2 estimates. Once you get uniform estimates for the second derivatives of your solution, then you can apply Evans and Krylov theory, Schauder estimates, and you can get estimates on derivatives of all orders. But you got to hit the C2 level. All right, C1 that you get from Vyachemovsky estimates are way below that. Okay. So what's going on? So it's some point earlier I said that, well, you know, if you look at these the sigma k curvature equations, the exponential nonlinear in the right-hand side is sort of critical, and then the nonlinearity on the left-hand side is subcritical. Well, that was for the positive cone equation. But for the negative cone equation, where you flip the signs, now something happens. Now the right-hand side is subcritical. All right, so this is a good sign. This is a terrible sign. So the quadratic nonlinearities are what destroy any hope we've had of getting any kind of, well, destroy any hope of getting a priori estimates, and therefore by conventional methods. I mean, this is what's making it difficult to get existence. Okay, so let me try to explain roughly what's going on with interior regularity. So Pengfei Guan and Wolfgang Wang proved local C2 estimates. These were later extended by Sophie Chen. She simplified the arguments, greatly generalized them. So the statement I want to give here very quickly is from her work. Okay, so these are incredibly useful when you want to try to prove existence in the positive case. So here's what they say. I want to state them in a somewhat general form because I want to emphasize the role played by this quadratic nonlinearity in the gradient terms. All right. So let's look at some general equation where you look at the k-symmetric function of the Hessian plus a general term here where I'm going to allow different numbers here. So say a coefficient A here and a coefficient B here, right? And then, but I'm going to make an assumption. I'm going to assume that the coefficient here is a negative number, and then the constraint on A is just this inequality, which you just have to sort of believe. Then it turns out you get the following estimate. Then if you control the right-hand side on a ball, say a unit ball, then you control up to second derivatives on the half ball, okay? So the crucial thing here, though, is this condition that the coefficient in front of this gradient term is negative. So for the positive cone equation, all right, so where your nonlinear Hessian is k-convex, what are the values? Well, A was 1 and B was -1/2. So you just check the conditions, they both work. And so these estimates hold. And as I said, they're crucial for the existence theory. On the other hand, if you look at the negative cone equation, because we replaced U with -U, all right, that flipped the signs on these quadratic terms. So now what happens is this B here is now positive, all right? So the assumptions are violated. So you don't get a priori estimates. Now you might say, well, maybe that's just a technical thing. All right, so these estimates don't work. That doesn't mean that the estimates don't hold. But it turns out something strange is actually going on. So Sheng and Schrödinger and Wang wrote down an example of a PDE that's structurally similar. It's not exactly the same as these PDEs, but they wrote down examples that they have the same kind of structure, and they showed that you can construct a sequence of solutions of their PDE on the unit ball so that the solution and its gradient were uniformly bounded along the sequence, but the Hessian blows up at the origin. So they're trying to explain that maybe you shouldn't expect local C2 bounds. Now, another reason to expect that something bad is going on here is the structural similarity between this negative cone equation and the transport equation in the theory of optimal transportation. Okay, so there's a long story behind this. I can't really get into it at all. I mean, I'm by no means an expert in optimal transportation anyway, but it turns out that for a certain choice of cost function that arises, for example, in the so-called antenna problem, the left-hand side of the transport equation looks like the sigma k curvature equation. And for this choice of cost function, it's known that it does not satisfy this Ma-Schrödinger-Wang condition, and therefore regularity is by example is known to fail. Okay, so there are other reasons why you would expect that maybe regularity is too much to ask for. Okay, so let me finish up very quickly by just saying a few things that are known, and then some things just at the very last minute or two, just ongoing work with Monaco Musso, where we're trying to do some kind of existence result. So are there any examples? Okay, yes. So Alice Chang and Zheng Chao-Han and Paul Yang decided to write down rotationally symmetric solutions of these PDEs on Euclidean space. And it turns out you already know one, and that is the hyperbolic metric. So the hyperbolic metric defined on the unit ball, it's rotationally symmetric. And as I mentioned before, the sigma k curvatures for hyperbolic space are constant. So this has got to be a solution to the negative cone equation, all right? So that's one rotationally symmetric solution. It only exists on some interval, right? Because it blows up at the boundary of the ball. But it turns out they also proved the existence of another solution. So I'll call it W subscript 1, WH for hyperbolic, W1 for this other one. It's also defined on a unit ball, and has two properties. The first is that it blows up at the same rate at the boundary of the unit ball as the hyperbolic metric. So near the boundary, it looks the same as the hyperbolic solution. But near the origin, you have a singularity in the sense that if you do a little expansion near the origin, this is what W looks like. So it's Holder continuous, all right, but it's not C1. The constraint here is that K is bigger than half the dimension, all right? So 2 minus n over K. You'll get Holder continuity, but you won't get differentiability. Okay, now, it turns out, this is interesting, and I think this is work, there's been recent work by Gonzalez-Li-Nguyen, and in some sense, their work kind of got me interested in thinking about this again, because the negative cone equation, there was so little progress for so long, I mean, I just sort of given up on it. But they decided to introduce a notion of viscosity solution. And so if you work with viscosity solution, now you got a fairly robust theory, right? Viscosity solutions are Lipschitz. So you have some kind of continuity, some kind of regularity built into the notion of solution. But the beautiful thing is you actually get existence, right? So for what they proved was a generalization of the well-known Loebner-Nuremberg result for the sigma k Yamabe problem, but for viscosity solutions. So Loebner-Nuremberg said smooth bounded domain in Euclidean space, you can always construct a complete conformal metric of constant negative scalar curvature. What they show is that you can solve the corresponding problem for the sigma k curvature equation, but your solution may just be a viscosity solution, right? It may not be regular. So, but contrast this with this this ODE solution of Chang-Han-Yang. What do you notice, right? So you have the hyperbolic solution. So if you take your bounded domain to be the unit ball, right? So we know we have the hyperbolic solution, right? But W1, this ODE solution, is also a solution, but it's not viscosity because it's not Lipschitz. Okay, so sorry, I'm running a little bit late. So let me just quickly say just a word or two about some ongoing work here. So the idea is that, look, these ODE solutions give us an example of a solution that's smooth away from a point, but at that point, it's only Holder continuous. So can you take those solutions and glue them into a compact manifold, right? So can you construct solutions that are smooth away from a prescribed set of singular points? And so this is something I've been working on with Monica. We want to take a compact hyperbolic manifold, take finitely many points, and then each point try to glue in one of these ODE solutions. So you should compare this with Shane's early work on the singular Yamabe problem, where he tried to take this, he had this sphere and he prescribed singular points for the Yamabe equation on the sphere. And so let me just say a couple of quick things here. I apologize for flying through the slides, but I just want to point, obviously we just want to do a gluing solution, a gluing construction, right? Take the ODE solutions, look at them along a cylinder, and then try to do a perturbation type argument. So anyway, the point is that you have one thing going for you and a lot of things going against you. The one main thing you're going for you is that the linearized operator is actually invertible in certain L2 weighted spaces. So that is incredibly important. What makes it very difficult is you're trying to glue two solutions that behave very differently. Right? So let me just, last dot here, I just want to say, what makes this kind of construction possible, though, is that this solution of Chang-Han-Yang, they come in families. So there's two parameters you have to play with. There's a dilation parameter that you have for the Yamabe equation, but then you also have what in the Yamabe equation, classical Yamabe equation amounts to is the Delaunay parameter. And it's this Delaunay type parameter in their ODE that allows us to match the hyperbolic solution to these singular ODE solutions to try to make the perturbation argument work. Okay, sorry for the rushing at the end, but stay safe and thank you very much.